Okay, we'll get started with section 11.2 here, which is called series. So the chapter is called sequences and series. Really, from 11.2 to the end of chapter 11, they're going to talk about series. Okay, so with a series, or an infinite series is what it is, we're going to take an infinite sequence and add the terms together. Okay, so you got a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, all infinitely many of these terms. I'm adding them together. Okay, here's summation notation. We're going to do a lot of things with summation notation over the next nine sections in the book. Okay, so I need the summation sign whenever I'm adding up a bunch of stuff, or the sigma sign. And then I always have bounds. So let's see, I'm starting at 1 and ending at infinity. So I'm going to go from n equals 1 to infinity, and what I'm adding up is a bunch of terms of the form a sub n. Okay, so then I replace n with the counting numbers. So when n is 1, a sub 1 is the first term. When n is 2, a sub 2 is the second term. When n is 3, a sub 3 is the third term, etc. Okay. Now there's a definition there. Next, it says that s sub n, which is equal to the summation as I equals 1 to n of a sub I, that's a sub 1 plus a sub 2. So all I'm doing is replacing the index I with counting numbers, starting at 1 and ending at n. So plus a sub 2 plus a sub 3 plus etc. And I'm ending at n, so the last term here is going to be a sub n. Now this sum is called the nth partial sum, okay, of an infinite series. If the limit as n approaches infinity of the nth partial sum, s sub n, exists, then the series is convergent. So if I add up all infinitely many of these terms here, I'll get an answer, which is going to be a finite number. Otherwise, s sub n is divergent. So if I add up all infinitely many of the terms, I get infinity. Okay? Yeah, so let's take a look at some examples here. In the first example, suppose that I have the summation as n equals 1 to infinity of 1 over 2 to the n power. Okay? Let me list out the first couple of partial sums here. So s sub 1 is just the first number. When n is 1, I get 1/2. S sub 2 would be when I add up the first two terms. So I get 1/2 plus, when n is 2, 1/4 is the next term. 1/2 plus 1/4 is 3/4. When n is 3, I'm going to add up the first three terms. So I got 1/2 plus 1/4 plus 1/8. 1 over 2 cubed is 1/8. And when I add up those three terms, I get 7/8. Okay, etc. S sub n would be where I add up the first n terms. Okay, so I got 1/2 plus 1/4 plus 1/8 plus 1/16 plus etc. all the way up to 1 over 2 to the n power, whatever n is. Okay? Now, from this pattern of numbers that I see here, it looks like whatever the denominator is, that's be 2 to the n power, the numerator is always going to be 1 less than that. Okay? So take 2 to the n power minus 1. So I see I get, here's 8, here's 7, here's 4, here's 3, here's 2, here's 1, right? So s of 4, that's going to be 15 over 16, right? Okay. Now the limit as n approaches infinity of s sub n, or the limit of the nth partial sum, is equal to the limit as n approaches infinity of 2 to the n minus 1 over 2 to the n. That's the same thing as 1 minus 1 over 2 to the n. And that's why I'd want to think about this, because the limit of a constant is always the constant. And as n is growing without a bound, the numerator will be growing without a bound. The denominator will be growing without a bound as the numerator will just sit at 1. So the corresponding fractions here are going to be getting closer and closer to 0. Okay, so I'm looking at 1 minus 0 is 1. Okay, so what that means here is that if I add up all infinitely many of these terms, the grand total is 1. Now, it's not approximately 1. It is equal to 1. Equal to 1. Okay, and I got a note here, the sequence a sub n, so if I had a sub n equals 1 over 2 to the n, that's going to converge to 0, right? Because the limit as n approaches infinity of 1 over 2 to the n, that's 0. Okay, so if I were to list out all infinitely many of these terms, 1/2, 1/4, 1/8, 1/16, etc., I'm getting closer and closer to 0 is what I'm saying. But if I'm adding up all infinitely many of those terms, that's a different question there. If I'm adding them all up, I get 1. Okay? Let's take a look at another example here. So in this next example, we have a situation with a telescoping series is what it's called. Okay, there's a couple of questions with telescoping series in this section. So what if I had the summation as n equals 1 to infinity of 1 over n minus 1 over n plus 1? Okay, well, let's list out the first couple of terms and see if I can come up with a pattern for S sub n. Okay, S sub n is different from A sub n. A sub n is 1 over n minus 1 over n plus 1, right? And S sub n is where I'm adding up all the terms. So S sub 1 would be just where I had the first term. That's n is 1. I got 1 minus 1/2. Okay, I'll keep the number in that form there. S sub 2 would be where I'd add up the first two terms. So I got 1 minus 1/2, and then plus when n is 2, I'm going to have 1/2 minus 1/3. The 1/2s cancel, and that's going to leave me with 1 minus 1/3. S sub 3 would be where I'd add up the first three terms. Okay, so I got 1 minus 1/2 plus n is 2 is 1/2 minus 1/3 plus when n is 3, I'm looking at 1/3 minus 1/4. Okay, there's negative 1/2 plus 1/2, those are gone. Negative 1/3 plus 1/3, those are gone. And that's going to leave me with 1 minus 1/4, etc. Okay, so just in terms of a pattern here, it looks like whatever the subscript is, I'm always going to be starting off with 1 minus a fraction, where the numerator is 1, and the denominator is always going to be 1 more than the subscript here. So or that's what I see from the pattern. You know, like here I got a subscript of 3, and the denominator is 4. Here I got a subscript of 2, the denominator is 3. Here I got a subscript of 1, the denominator is 2, right? So whatever the subscript is, n, the denominator is going to be n plus 1. Okay? Then the limit as n approaches infinity of S sub n, I want to know, does this series converge or diverge? Okay, so that's why I'm figuring out this limit here. That's equal to the limit as n approaches infinity of 1 minus 1 over n plus 1. Limit of a constant is always the constant. And the limit as n approaches infinity of 1 over n plus 1, that'd be 0, right? Because n is growing without a bound. The denominator is growing without a bound as the numerator just sits at 1. So the corresponding fractions are going to get very minuscule, closer and closer to 0. 1 minus 0 is 1. Okay, so in other words, if I add up all infinitely many of these terms here, the grand total is going to be exactly 1. Or this series is going to converge to 1. Okay. Let's try another example here. So the next one, what if I had the summation as n equals 1 to infinity of 3 over n times n plus 3? Okay, this would be another situation where I've got a telescoping series. So what I did to start is I rewrote this series, or the sequence part in the series, in the form of where I'm subtracting two fractions, okay? And how I'm getting that is by using partial fractions. So we saw this in section 7.4. 3 over n times n plus 3. Well, n and n plus 3 are both linear factors, right? So I'm going to have a over n plus b over n plus 3. I got to find a and b. Well, if I clear out the denominators here, multiply both sides by n times n plus 3, then 3 would be equal to a times n plus 3 plus b times n. The n plus 3 is a cancel, right? So a times n plus 3, that's a times n plus 3 times a, and then plus b times n. Okay, if I group the n terms together and then the constants together, I'm looking at a plus b times n plus 3a, that's a constant. Okay, so then I'm going to match the coefficients on both sides of this equation. I don't have any n terms on the left, right? So a plus b is equal to 0, and then 3a is equal to 3. Well, if 3a equals 3, then a is 1. And if a is 1 and a plus b is 0, then b would be negative 1. Okay, so in this form here, 3 divided by n times n plus 3, that's the same thing as 1 over n minus 1 over n plus 3. Okay, and now this problem here is going to be very similar to what we just saw right here. Okay, so let me come up with a pattern, S sub n, and just look at the first couple of terms here. So S sub 1 would be where I add up the first term. When n is 1, I get 1 minus 1/4. And then when n is 2, I'm going to add the first two terms. So 1 minus 1/4 plus, when n is 2, I get 1/2 minus 1/5. Okay, and then S sub 3 would be where I'd add up the first three terms. So I'm looking at 1 minus 1/4 plus 1/2 minus 1/5 plus, when n is 3, I get 1/3 minus 1/6. Okay, when n is 4, I'm going to add up the first four terms. So I got 1 minus 1/4 plus 1/2 minus 1/5 plus 1/3 minus 1/6 plus, when n is 4, I'm getting 1/4 minus 1/7. Okay, here's negative 1/4 plus 1/4, those are gone. S sub 5 would be where I'd add the first five terms. So I've got these same first four terms that I had in S sub 4, and then when n is 5, I get 1/5 minus 1/8. Okay, the 1/4s are gone, and then here's negative 1/5 plus 1/5, those are gone. Okay, etc. So then S sub n, it looks like the only terms that are not going to cancel, you know, if I were to keep going here, find S sub 6, S sub 7, right? Like I'm always going to have some things canceling. Like the 1/4 is always going to be gone, the 1/5 are going to be gone, 1/6 will be gone, right? Etc. So it looks like, but I'm always going to be starting off with 1 plus 1/2 plus 1/3. And then I'm going to be subtracting, let's see, 1 over 6. So that, you know, in the substitute there was 5. So it'll be 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3. That's what I see in this pattern. When I got 1 plus 1/2 plus 1/3, and then 5, that's 1 more than 4, 6, and then 7. Okay, so this would be the kind of the general formula that I'm getting for S sub n. Then the limit as n approaches infinity of S sub n, that is equal to the limit as n approaches infinity of 1 plus 1/2 plus 1/3 minus 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3. These three terms are going to go to 0. So then 1 plus 1/2 plus 1/3, that would be the same thing as 11/6. Okay? So what I'm saying is that if I add up all infinitely many of these terms, I got infinitely many numbers that I'm adding together, the grand total is exactly 11/6. Okay, so this sequence, this series is going to converge to 11/6. Okay. Now the other part of this section is we're working with a geometric series. Okay, so we'll talk about that in the next video here.